Hello, everybody. I want to go over CompTIA A Lesson 1 with the resources and some of the readings that are involved with Lesson 1 in CompTIA A. So let's go ahead and get started. So I'm going to switch into a full view here. So what you see here is essentially the breakdown of lessons. We have Lesson 1, Lesson 2, 3, 4, 5, 6. 1 through 10 is essentially the core one, with lesson 1 being installing motherboards and connectors, followed by installing system devices. What we're going to do is focus solely on installing motherboards and connectors. So let's go ahead and take a look. Within installing motherboards and connectors, you're going to see that there is an overview of the A+ Core 1 and Core 2 and how to use this particular software. But I'm going to hop right to the introduction and core objectives of Lesson 1 and the topics related to installing motherboards and connectors. And one of the key parts as you review each lesson with CompTIA A is always to understand the categories and topics in each lesson and the objectives. So here you have explain cable types and connectors, install and configure motherboards, and explain legacy cable types. So just remember, when you hear the term legacy, that is an older version of technology, an older type that may need to be updated to be able to use, that is used on an older piece of technology. So just remember what legacy means. Now with motherboards, we're going to learn how to install and configure the components of motherboards. We're going to look at cable types and connectors. So let's just take a quick look at what they say here. As an IT professional, you will set up desktop computers and help end users to select configuration and peripheral devices that are appropriate to their work. You will often have to connect peripheral devices using the correct cables and connectors and install plug-in adapter cards. So you're going to get an overview of how to do that. So here we can rate our confidence, but I'm just going to hit continue. And once we're into topic A, we're looking at a first of our core 1 objectives covered. So explain basic cable types and their connectors, features, and purposes. So a PC is made up of different components. All of these components need to be able to communicate with each other so the computer can function properly. If you can distinguish connection interfaces and connectors quickly, you'll be able to support users by installing, upgrading, and replacing PC peripherals efficiently. So that's all about, hitting those core 1 objectives with topic 1A. And as we kind of keep going through, we're going to see personal computers and the definition of personal computers. The components of our personal computer are divided between those that are designed to be handled by the user, peripheral devices, and those that would be damaged or dangerous if exposed. Peripheral devices typically perform the function of input, keyboard, mouse, microphone, and camera, output, monitoring speakers, or external storage. The system case chassis houses the internal components. These include the motherboard, central processing unit, system memory modules, adapter cards, fixed disk, and power supply unit. Most cases use a tower form factor that is designed to be oriented vertically and can be placed on a desk on the floor. So a couple of key words that you just want to start to recognize here is this definition here. Central processing unit, CPU, system memory modules, adapter cards, fixed disk, and power supply unit. And they talk about how they can also be purchased as all-in-one units. And we're introduced to the PC case in order to perform maintenance. So they have the overview of a tower case and how the front panel provides access to removable drives, and that the tower case has a side cover that can be removed by sliding the panel from its housing. So interestingly enough, that is one of the lesson questions for this chapter, is how to access the side case. And you can see the front panel provides access to the removable drives, a power on-off switch, and a light-emitting diodes to indicate drive operation. So they provide an overview here: optical disk drive, unused optical disk drive bays, the front input-output panel, the power button, potentially the temperature display on the case, air vents for airflow, and then an overview of the back with the power supply with the fan, the chassis fan airflow cutout, the motherboard I/O panel, an expansion card slot in use, expansion card slot not in use. So the difference of what one looks like in use and not in use. And also how you can see the Ethernet port with the motherboard I/O panel here, items that connect to the motherboard. So there's just an overview of those components, like the power supply unit, the connections to the motherboard, the I/O port areas, and the slots. So here are a couple important elements to remember. So the I/O shield and blanking plates are necessary to prevent gaps in the system case. Gaps create the following problems. Components are more exposed to touching, increasing risk from electrostatic discharge, ESD. We also have pins in the I/O shield connect the external metal parts of the ports to the metal case, which is in turn bonded to the PSU, which connects to the building's ground system when plugged in. This provides a safe path for ESD to drain into instead of arcing to a chip. Components are more exposed to electromagnetic interference, EMI. EMI is energy from magnetic and electrical sources, and this can cause temporary or permanent faults. So that's just an introduction to the front and back of a PC and the personal computers. Now let's move into peripheral devices. An input-output I/O port allows the device to be connected to the PC via a peripheral cable. Some ports are designed for a particular type of device, such as a graphics port, or to connect to a monitor. Other ports support a variety of device types. External ports are positioned at the rear of the PC through cutouts in the case. So here we see I/O port area, and we have the HDMI input, the DVI, the SATA, two different locations, USB, RJ45 network, and audio ports. Interfaces, ports, and connectors. A hardware port is the external connection point for a particular type of bus interface. A bus allows the transfer of data to and from the device. The connector is part of the peripheral cable that can be inserted into a port with the same shape or form factor. So here we have, for example, the portable hard drive with a micro USB port with a micro USB connector, the cable going into a 3.0 port from a 3.0 device, from a 3.0 cable into the tower. So 3.0 connector into the 3.0 port that's in the I/O port of the area of the PC. Binary data and transfer storage of units. When comparing bus interfaces, it's important to use appropriate units. Computers process binary data. Each binary digit or bit can have the value 1 or 0. Storage is often measured in multiples of 8 bits, referred to as a byte. A lowercase b unit refers to a bit, while uppercase means a byte. Transfer rates are in units per second. So 1,000 kilobits and kilobytes, 1,000 times 1,000 megabytes or megabytes MB /S, and 1,000 times 1,000 times 1,000 gigabits, and gigabytes. USB, Universal Serial Bus Cables. So the universal serial bus is the standard means of connecting most types of peripheral devices to the computer. USB peripheral device functions are divided into classes such as human interface, keyboard and mice, mass storage, disk drives, printer, audio device, and so on. A USB is managed by a host controller. Each host controller supports multiple ports attached to the same bus. In theory, there could be up to 127 devices per controller, but to overcome the limitations of sharing bandwidth, most PC motherboards provision multiple USB controllers, each of which has three or four ports. So here's an overview of the USB standards, which is an important element of understanding in this section in lesson 1. And they are saying here that there are multiple iterations of the USB standard. Iterations of USB 3.x introduce new connector form factors and upgraded transfer rates, each of which are full duplex, so a device can send and receive simultaneously. USB 3.2 deprecated some of the older terms used to describe the supported transfer rate. So here they just have a breakdown of the speed of 5 gigabytes per second, what type of connectors had that connection speed, legacy designation, and the standard was USB 3.2 Gen 1 super speed USB. And then we have the 10 gigabytes per second, and this is the 3.2 Gen 2.1 super speed USB, gigabytes per second, and the USB-A, USB-C, and USB micro. And the legacy designation being 3.1. And then here we have the USB 3.2 Gen 2 times 2 super speed USB, 2 times 10 gigabytes per second with USB. So USB 3 controllers feature 2 subcontrollers. One controller handles super speed capable devices, while the other supports legacy high speed, so the older version of high speed devices, full speed and low speed USB version 1.1 and version 2 devices. Consequently, legacy devices will not slow down super speed capable devices. So that, and here we look at just the types of USB connectors, which we're probably all familiar with in terms of USB connector types. We have the type A for connection to the host, type B for connection to large devices such as printers, type B mini, a small peripheral device connector, type B micro, such as smartphones and tablets, distinctly flatter than some of the older ones. And then we also have type A, type B micro, and type C. In USB, a USB cable can feature type A to type A connectors or can convert from one type to another, type A to type B, or type A to micro type B, for instance. In USB 3, there are new versions of the type A, type B, and type B micro connectors with additional signaling pins and wires. USB 3 receptacles and connectors often have a blue connector tab or housing to distinguish them. So here we get into USB 3.1 defines the USB-C connector type. The maximum cable length for low-speed devices is 3 meters, while for full speed and high speed, the limit is 5 meters. Power. As well as a data signal, the bus can supply power to the connected device. Most USB Type A and Type C ports can be used to charge the battery of a connected device. HDMI and DisplayPort video cables. So the USB interface supports many different types of devices, but has not traditionally been used for video. As video has high bandwidth demands, it is typically provisioned over a dedicated interface. The cable bandwidth is determined by 2 main factors: The resolution of the image measured in horizontal pixels by vertical pixels. For example, 920 by 1080 is a typical format of high definition video. And it's often known as high definition. And 3840 by 2160 is a typical of a 4K video. Speed at which the image is redrawn, measured in hertz, or frames per second. As examples, uncompressed HD video at 60 frames per second requires 4.5 gigabytes per second, while 4K at 60 frames per second requires 8.91 gigabytes per second. Computer displays are typically of the liquid crystal display, LCD, thin film transistor type. Each pixel in a color LCD comprises cells with filters to generate the three additive primary colors, red, green, and blue. Each pixel is addressed by a transistor to vary the intensity of each cell, therefore creating the gamut, the range of colors that the display can generate. The panel is illuminated by a light-emitting diode, LED array, or backlight. An LCD TFT is often referred to as a flat panel display. They are also called LED displays after the backlight technology. Older flat panels use fluorescent tube backlights. High definition multimedia interface. The high definition multimedia interface, HDMI, the digital audio interface developed for both use on both consumer electronics and computer equipment, is the most widely used video interface. It is ubiquitous on consumer electronics such as televisions, game consoles, and Blu-ray players, as well as monitors designed for use with PCs. HDMI supports both video and audio, plus remote control and digital content production, HDCP. Updates to the original HDMI specification have introduced support for higher resolutions such as 4K and 8K, and gaming features, such as the ability to vary the monitor refresh rate to match the frame rate of the video source. The support for the audio, of course, is helpful. Most TVs and monitors have built-in speakers. The video card must have an audio chipset for this to work. So, the HDMI supporting both is a huge benefit. There are full-size Type A, mini Type C, and micro Type D connectors, all of which are beveled to ensure correct orientation. So you can see the bevel is similar, they're just different sizes. So here's like the mini HDMI example. And then we have the DisplayPort interface. HDMI was developed by the consumer electronic companies and requires a royalty to use. DisplayPort, which is developed by VESA, supports some cross-compatibility with DVI and HDMI devices. And it was developed as a royalty-free standard by the Video Electronic Standards Organization, which is an organization that represents PC, graphics adapter, and display technology companies. Basically as another option, beyond HDMI. One of the main advantages of DisplayPort over HDMI is support for daisy chaining multiple monitors to the same video source. Using multiple monitors with HDMI requires one video card port for each monitor. And here we go with Thunderbolt and Lightning cables. So the Thunderbolt cable can be used as a display interface like DisplayPort and as a general peripheral interface like USB 3. The latest version uses USB-C connectors. The Lightning is a proprietary interface used by Apple iPhone and iPad devices. SATA hard drive cables. So here we have the Serial Advanced Technology Attachment Interface. Serial ATA is the most widely used interface for hard disks. On desktop and laptop computers, it uses a 7-pin data connector with one device per port. There are 3 SATA connectors, 3 SATA standards, and specifying bandwidths of 1.5 gigabytes per second, 3 gigabytes per second, and 6 gigabytes per second, respectively. SATA drives also use a new 15-pin power connector, though adapters for the old-style 4-pin Molex connector are available. External drives are also supported via the eSATA interface. So as we click off this definition, you see the data cable, the power cable with SATA connections. The 7-pin connector does not supply power. A separate 15-pin SATA power connector is used to connect the device to the PC's power supply. So here we have a view of what the front view of 6 SATA ports look like, with the legacy PATA IDE port. And then we have Molex connector, a legacy power connector for internal devices such as hard drives and optical drives. And then we have the external SATA, a variant of SATA cabling designed for external connectivity. All right, now we're into 1B. So as we shift into 1B, it's important to give yourself a little break, take some notes potentially around some of the areas we covered, the vocabulary, the topics around motherboards and connectors, and what we've learned so far. As we move into this next section of the very first lesson, we're going to go a step deeper. And the great thing that CompTIA A does is it enables us to go deeper and deeper within each lesson, and it builds a framework. So within lesson 1, what it's trying to get us to do is understand the parts of the computer and how different devices connect to it, such as peripherals, what those connections look like, and why they're important. So as we get into this topic, we're going to go ahead and switch back over. We have the core 1 objective, which we really always need to focus on within any single lesson, is given a scenario, install and configure motherboards, central processing units, CPUs, just as we learned in the first chapter, and add-on cards. So let's talk about the function of the motherboard. So all computer software and data are processed by using the 1s and 0 of binary code, which ends up being one of the assessment questions. Software works by running instructions in the central processing unit. This can be referred to as the compute or processing function of a PC. Instruction and data also require storage. The CPU can store only a limited number of instructions internally at one time. So that's essentially what this diagram begins to start to show. Additional storage for running programs and open data files is provided through system memory. This random access memory, the RAM, storage technology is non-persistent. Non-persistent means that the RAM device can only hold data when the PC is powered on. Mass storage devices are used to preserve data when the computer is turned off. So mass storage devices are like CD drives, mass storage drives like hard drives, SSD drives. RAM is that non-persistent volatile memory. So as a system is processing information on the CPU that you see here, and it also has cache memory, it's utilizing RAM with its brain of the computer to process data as well. But ultimately, when data is being stored within the computer, it's being stored on the mass storage device or removable storage device, it's not being stored permanently on the RAM memory. So just remember that RAM is memory. RAM is memory, but is not memory, which is actually storing data. And when the computer is turned off, memory that is on the mass storage devices stays there. Memory that's on the RAM disappears. So it needs power to maintain itself. And the great thing about this graphic is it has the most volatile and the least volatile. So it also says fastest and slowest. So in terms of speed, definitely CPU, RAM, the cache memory, when some of the slowest reading memory is those SSDs, those mass storage devices, and some of that removable storage. The motherboard system clock synchronizes the operation of all parts of the PC and provides a basic timing signal for that CPU. Clock speeds are measured in megahertz or gigahertz. Clock multipliers take the time signal produced by the generator and apply a multiplication factor to produce different timing signals for different types of buses. This means that one type of bus can work at a different speed or frequency to another type of bus. The motherboard also influences the system speed. They can be upgraded. So here's a section on electrical safety in ESD. So it is important to understand electrical safety when working with computers, of course. Means, when working on a computer, it should be powered down if you can, and disconnecting and drained of a charge. Electrostatic discharge is when, let's give you a great definition of this. Components such as a CPU, system RAM, adapter cards, and the motherboard itself are vulnerable to electrostatic discharge, ESD. This is when a static charge stored in your clothes or body is suddenly released into a circuit by touching it. Handle components by their edges or plastic parts and ideally use an anti-ESD wrist strap and other protective equipment and procedures. So here's an ESD rib strap on an ESD mat so that when working on the computer, it takes the charge off of the human body. And it will be covered again in personal safety in the Core 2 course. So here we're getting into the motherboard, CPU, and system memory connectors. All motherboards have a variety of connector types and socket types for the system devices: CPU, memory, fixed disk drives, and adapter cards. So here we have the slots for the RAM, memory slots, the disk drive connectors, adapter card slots, the I/O ports, and also the socket for the central processing unit, that CPU. The brain of the computer goes right here with the CPU. That RAM memory goes into the memory slots here. We have the spot for the disk drive connectors and adapter cards, and then the ports. New motherboards are generally released to support the latest CPU models. Most PC CPUs are manufactured by Intel and AMD. These vendors use different socket designs because CPU technology changes rapidly, given a motherboard will only support a limited number of processor models. System memory uses a type of memory technology called random access memory. Program code is loaded into the RAM so that it be accessed and executed by the processor. RAM also holds data such as the contents of a spreadsheet or a document while it's being modified, while it's being changed. System RAM is volatile. It loses its content when power is removed. An important feature here is known as dual inline memory, this DIMM, fitted to a motherboard slot. A DIMM slot has catches at either end and is located close to the CPU socket. It is numbered and often color-coded. These successive generations of RAM technology, such as DDR3, DDR4, and DDR5. A DIMM form factor is specific to a particular DDR version. Motherboard and storage connectors. Here we have the review of the SATA, the Serial Advanced Technology Attachment Interface. The motherboard contains several SATA attachment ports that connect one or more fixed drives. SATA can also be used to connect removable drives, such as tape drives and optical drives. And they're installed to a drive bay and connected via SATA power or a Molex connector. An M2 interface, an SSD, can be provisioned in an adapter card form factor. These are often used in M2 interface. An M2 port is orientated horizontally. The adapter card is inserted at an angle, then pushed into place and secured with a screw. And there's a photo here. And then we have the external eSATA. It's a variant of SATA cabling designed for external connectivity. So here we get into motherboard adapter connectors. So peripheral component internet connect express interface, PCIe bus, is the mainstream interface for modern adapter cards. It uses point-to-point serial communications, meaning that each component can have a dedicated link to any other component. So here we have the times 16 PCIe slot, the times 8 PCIe slot, times 1 PCIe slot, and the regular PCIe slot. And internal expansion bus that uses serial point-to-point communication between devices. Each link can comprise one or more lanes, times 1, times 2, times 4, times 8, times 12, times 16, or 32. Each lane supports a full duplex transfer rate of 250 megabytes per second, up to about 4 gigabytes in the version 5. So here we have the breakdown of the speed of the point-to-point. And we get into the PCI component, peripheral component interconnect. That's a legacy internal expansion bus supporting 32-bit parallel transfers working at 33 megahertz. PCIe is software compatible with PCI, meaning that PCI ports can be included on a PCIe motherboard to support legacy adapter cards, but PCI cards cannot be fitted into PCIe slots. So as with many legacy technologies, and we understand the word legacy now, it's older technologies, uses parallel communications. Most types of PCI are 32-bit and work at 33.3 megahertz, achieving a transfer rate of up to 133 megabytes per second. That is 32 bits divided by 8 to get 4 bytes, then multiplied by the clock rate of 33.3. So here's the breakdown. The 5 volt, 3.3 volt, and the dual voltage 32-bit PCI sound card is what this is. So it's a 32-bit PCI sound card with dual voltage. So in terms of form factors, when you hear the word form factor, that means the shape and the size and the format in which a piece of hardware comes. So with motherboards, the main one to remember right now is the ATX. The standard PC case, motherboard, and power supply specification. There are mini, micro, and flex ATX specifies smaller board designs. So they do go over the full size is 12 by 9 inches with 7 expansion slots. The micro specifies a 9.6 square board, so 9.6 times 9.6. And then we have the Information Technology Extended Form Factor, which is a series of motherboard form factors designed for small form factor computers and appliances. The mini ITX is 6.7 inches square with one expansion slot. These are designed for small cases. So here's a section on motherboard installation, how it's attached by using standoffs so that it holds itself firmly on the motherboard to the case. So there are labs to help you understand better the actual physical attachment of the motherboard to the case. Check whether any jumper clips need to be adjusted. A jumper is placed over any header pins. Orient the board to the oblong input output. So you're matching the input output ports to the shape of the case. You're going to utilize the standoffs to make sure that the hole locations match up. You're going to add the CPU and memory modules to the motherboard before installing the board in the case. You're going to check the alignment of the standoff locations again and verify each standoff is secure, because sometimes items will shift. So here you see in the photo is a screwdriver person basically on the corner of the motherboard, either removing or screwing down one of the screws that attaches the motherboard to the case. Motherboard and header power connectors. So motherboard and header power connectors, here we have additional slots and other sockets on the device. We have the front panel headers, 9-pin USB headers, and also audio headers for connections. Headers are components on the front and rear panels of the case connect to headers. Connector on the motherboard for internal cabling such as fan power, front panel ports, and buttons. The power button sends a signal interpreted by the OS as a command to shut down rather than switching off the PC. The drive HDD has activity lights show when an internal drive is being accessed. Audio ports allow speakers and or headphones. USB, internal USB 2.2 connections are made via 9-pin headers, which accept up to 2 4-pin port connectors. The 9th pin is to orient the cable connect correctly. USB 3 headers use a 2x10 format and can be inserted by 2 ports. When disassembling the system, you should make a diagram of the position orientation of the header connectors. Power connectors. The motherboard also contains various connection power points for the power supply and fans. The main motherboard power connector is a distinctive 2-pin by 12-pin block with square pin receptacles. The fan connectors are 3 or 4-pin Molex KK format. There will be one for the CPU and one more for the case fans, such as memory and video adapters. 4-pin fan connectors support precise fan speed via a pulse with modulation. Signal carried by the blue wire 3-pin fans are controlled by varying the voltage. So here we are in video and capture cards. So a video card is an adapter that handles graphics processing and output to a display device over one or more of the video interface ports. So we talk a little bit about the most common ones like NVIDIA, ATI, AMD. With an add-on card or a PCIe slot. They provide graphics processing unit, GPU, a microprocessor designed and optimizing for processing instructions, for rendering 2 and 3D images and effects on screen. The graphics memory 3D cards need a substantial amount of memory for processing and texture effects. A dedicated card may be fitted up to 32 gigabytes of GDDR RAM at the high end. Around 8 gigabytes would be more typical of current mid-range performance cards. Low-end cards use shared memory. That is, the adapter uses the system RAM. Some cards may use a mix of dedicated and shared. And video ports, the type and number of connectors such as HDMI, DisplayPort, and Thunderbolt. So here we have a graphics video card with the DisplayPort ports, the HDMI ports, and the DVI ports attached to it. A graphics card is where it generates an output video signal to drive to a monitor used to record video input and save it as a type of movie or streaming media file. And then we have sound cards. So sound cards, audio playback is achieved via a speaker or headphones would connect to a sound card. A sound card, adapter card providing sound playback and recording functionality. A number of different audio ports exist on modern computer motherboards or on specialist sound cards. Commonly, audio ports may be marked as audio out and audio in, speaker out, microphone input, mic, and headphones. So on a sound card, you're going to have audio in, you're going to have a mic in, audio out. So basically cards that process audio, often with a 3.5 mono or stereo jacks. Then we have network interface cards, NIC cards. Adapter card that provides one or more Ethernet ports for connecting hosts to a network so they can exchange data over a link. So it essentially has an RJ45 port, which can allow this card to connect to the network. And this is the network interface card. Which gets installed and then allows the connector to have a dedicated network connection. And then we're going to get into legacy cable types. So before we get into legacy cable types, let's take a deep breath. Think about what we just reviewed there in terms of adapters, graphics cards, sound cards, networks cards. Those are adapters to hardware and parts of the motherboard, parts of the system that allow the computer to process sound, video, and a range of other, resources when it's connected. So, as we move into the next step, we're really looking at some of the legacy connection types that we want to think about are still out there as we're continuing to learn about computers and how there are different types of connectors. So the goal here is to explain basic cable types and their connectors, features, and purposes. So we have DVI and VGA video cables. So the digital video interface, legacy video interface that supports digital only or digital and analog signaling. That's the DVI. DVI is no longer an active deployment. You are only likely to encounter DVI on older display devices and video cards. So just keep that in mind. And also remember that with DVI and VGA video cables, older interfaces were used when computer monitors and projectors were predominantly of the cathode ray tube CRT type, driven by an analog signal. There are 5 types of DVI supporting configurations for single and dual link extra bandwidth and analog digital output signaling. The pin configuration of the connectors identifies what type of DVI is supported by a particular port. So we have the DVI-D, single link, DVI-I, single link, DVI-D dual, DVI-I dual, and the DVI-A. And then we have the VGA, a very common old legacy that you might see out there on older computers. Legacy video interface supporting analog only signaling over a 15-pin D shell connector. So you'll see these usually just transporting video on older devices, 1920 by 1080 depending on cable quality. Small computer system interface. So this is a legacy expansion bus standard allowing for the connection of internal and external devices. Each device on an SCSI bus must be allocated a unique ID. The bus must also be terminated at both ends. It's an example of a legacy parallel bus. Can control multiple devices by internal ribbons. It can be used by internal and external devices, and with the male 68 pin and the female 68 pin. And then we have integrated drive electronics interface. So here we have the definition: a legacy mass storage bus, most commonly implemented as extended IDE, EIDE, and also referred to as a parallel advanced technology attachment, PATA, parallel advanced technology attachment. Each IDE controller port supports 2 devices connected over a ribbon cable with 3 connectors: controller, primary device, and secondary device. So an EIDE cable typically has 3 color-coded connectors. The blue connector is for the motherboard, the black and gray connectors attached to devices 0 and 1 respectively. When inserting a connector, pin 1 on the cable must be orientated with pin 1 on the port. On the cable, pin 1 is identified with a red stripe. The connectors are also keyed to prevent them from being inserted the wrong way around. Red stripe indicates pin 1. Then we have serial cables, another older port. The serial port is a legacy connection interface where data is transmitted over one wire, 1 bit at a time. Start, stop, and parity bits are used to format and verify data transmission. The interface is also referred to as the recommended standard number 232, RS-232. While modern interfaces like USB are also serial, an RS-232 interface uses much less sophisticated signaling methods. Consequently, an RS-232 serial port supports data rates up to 115 kilobytes per second only. So this is a legacy connection where data is 1 bit at a time, much older connection, usually associated with connecting external modems. The DB9 here mentions legacy connector form factor for used for serial 9-pin and VGA 15-pin interfaces. And then we have adapter cables. So adapter cables, given the numerous types of cables and connector types, often be the case that basic peripherals will not be able to provide a connection between a port available on a PC and the port used on a peripheral device. So if I click on adapter cable, it's a peripheral cable converting between connector form factors or between signaling types, such as DisplayPort to HDMI, so that the different types of devices can work together. Examples provided here include video adapters between signaling types such as HDMI to VGA, HDMI to DisplayPort, or HDMI to DVI. USB adapters to convert connector types such as USB-C to USB-A, and there are also USB hubs that provide additional ports. USB adapters to various kind of output, including Lightning and HDMI. So just the awareness that there are existing adapter cables, so that they're existing out there. So that is the end of lesson 1 content. So, that is the final component of, going over legacy connectors is the third part of lesson 1. So lesson 1, just to go over and do a quick review of the sections, and I'll flip through. Just flip through here slowly. We'll do a quick review. First we have lesson 1, which is all about motherboards and connectors. And we talk about explaining the types of connectors and their purpose, and the parts of personal computers. We talk about peripheral devices and how they connect to the device. We discuss USB cables and the different types of speeds and cable interfaces. We go over HDMI and DisplayPort video cables, Thunderbolt and Lightning cables. And then we have SATA hard drive cables and how they connect the data or power cable and legacy ports versus SATA ports. And then we move into topic B, and that is building on the understanding of those cables. Now we're going to look at the motherboard itself. So the exam objective here covered is given a scenario, install and configure motherboard, central processing units, and add-on cards. So we're going to get a little deeper into the actual components of the motherboard. So here we talk about the difference between RAM and mass storage devices, and how RAM is non-persistent, but it's faster, but it requires power, where mass storage doesn't require power, can be included in removable storage or on a hard drive, but not in RAM itself. Then we get into the electrical safety and ESD, the electrostatic discharge, and they go over the ESD wrist strap and the value of removing the charge from our bodies when we work on computers. And then there's the motherboard, CPU, and system memory connectors. So how the CPU socket, where that's located, the memory slots, the disk drive connectors, the I/O ports, and additional adapter card slots. And then storage connectors like SATA M2 interface and the external SATA interface. So how storage is connected to the motherboard. And then the adapter connectors like PCIe and what the nature of those are and the speeds through these ports. And also the PCI legacy format is included with that. Then we have the motherboard form factors such as ATX, micro ATX, the information technology extended form factor, mini ITX, square, and then the installation of the motherboard, the location of pins and standoffs, and the important part of what to consider when installing or removing a motherboard. Motherboard headers and power connectors. The front header locations, the 9-pin headers, the audio headers. Video cards and capture cards, what a video card is, what's a capture card, the importance of them with different video quality and processing. Sound cards, network interface cards, and the NIC cards. And then the final section, of course, is the legacy cable types, the DVI and VGA cables, the small computer system interface cable, the IDE system integrated drive electronics interface, the serial ports and serial cables, and how important adapter cables are to making older cables work. So thank you for hopping on and joining me as we review lesson 1. In future videos, I'm going to be going over the lesson questions for this section and go over the questions that are connected to lesson 1. As you continue to develop your knowledge, just keep an eye out for the lesson 1 questions video and how you can then review the content we just covered. So thanks for joining Digital Futures Education. Appreciate your time and look forward to connecting with you soon.